All right, so this is the midterm review. As announced last week and repeated this morning, the midterm has been going on since 12:01 a.m. I see about 15 or so folks have already submitted something, maybe all of it. But in any case, you have until midnight tonight, minute before midnight tonight. So you have a very generous 24-hour window. It's the same format as exam one, programming exercises that you submit through the hand-in. We've got starter code here, and here's the handout telling you exactly what we're expecting. There's no collaboration with any individual. All must be your own work. We will be running MOS through. I've already run it on the dozen or so that they're in there, and we'll continue running it throughout the day. That's our measure of software similarity. So make sure that you are not collaborating with anybody in any way. We are having lecture this day, today, right now, but this is completely optional. We're going to be going over our previous midterm from spring 2022. All right, so just last semester here. Any questions before we start? No? Okay. Well then, again, we are live, so if you have any questions, you can go ahead and post to the YouTube live stream here. So the first exercise that we have is very similar to that review that we already did right after, I think it was hack 6 or so, where you have one input value here, joule, which is a measure of power, right? A measure of energy. And you want to convert it to 3 other values, calories, BTUs, and foot-pound force right here, using these conversion values right here, okay? So these 3 values are all passed by reference because we want to convert to all of them. You can't return 3 values from a function, but you can pass 3 variables by reference and get 3 results from a function. The integer return value here is going to be used for non-zero error handling, right? The non-zero value to indicate an error, and a 0 value to indicate that there was no error, right? I think when we gave this, we gave some additional, like a tester function here. We're going to write our own testing functions as we go along. Just as a preview here, we've got 3 other functions that all operate on arrays. Right? So let's go ahead and do this one first. Right? I'll go ahead and create files here. I'm just going to go ahead and put them all into the same files, like midterm.h, midterm.c, and we will want to be testing this, so midterm tester.c. Right, there we go. And there they all are. So if I'm going to start out in the H file here, well, what's the very first thing I should be doing in any of my files? I should make a what? Documentation, and in this case, we mean an author header, right? I started grading midterms on the other sections, and I mean, they're very, very good, and in a lot of cases, like 100%, 100%, 100%, except they're losing 1 point because there's no author, right? It's like turning in an essay with no name on it, okay? So author me, right? And of course, if I'm going to put in a prototype here, what else belongs above the prototype? Document, right? I'm not going to do that. I'll leave that as an exercise for you. But it's an easy way to lose 1, maybe 2 points here, right? So make sure that you're doing that. Yeah. Go ahead.
So, would you be your, author page in the header file?
It depends. The standard that we're using is that at least one of the files needs an author header. It is most natural to put it in the header file, or at least one of your source files, period, needs an author header. And it's natural to put it in H because in the header file, because that's where your other documentation is. Right? If you want to put it in every file, that's perfectly fine too. Right? Again, in real life, these would probably be auto-generated, that you would have some sort of an annotation here, like insert copyright, right? There we go. And then you'd have some other tool to come in and replace that with an actual copyright notice automatically, right? Anyway, let's go ahead and implement this function now. When I do functions, what is the very first thing I should be doing? Error handling. And among error handling, what is the very first error handling should I be checking? Null pointers, right? If calories is null, or BTU is null, or foot-pound force is null, right? Then all of these are an error. You cannot dereference them. This is the improper way of checking for null. I've taken that pointer variable and I've transformed it into a regular variable. Regular variables aren't null. Only pointers are null, okay? Return, I don't know, non-zero error code, we'll just go with 1 here. If you want to go back and put in defines, right? Define null error as 1, right? Or if you want to create your own enumerated types, right? Type def enum, no error, etc., 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 right? Go ahead and do that. Right? All right. What else could go wrong here? Are there any other error conditions that we need to be aware of? Yeah, can you have negative energy? You can have negative relative energy from a high energy system to a low energy system, right? You can have a current, it's not flowing backwards, it's just going from high energy to low energy, right? But in general, you cannot have, else if, joules is less than 0. You can't have negative values. So return, I don't know, some other error code too. Now, also part of error code error handling, right? At the very end, what should you return if there's no error? Don't forget that, right? 0. Otherwise, you can go ahead and do your work now. Calories is equal to joules times, what's that conversion rate? Whatever that is, right? Cut and paste, right? If you want to, you can go ahead and put this into a constant global variable. You can put it into a define macro. You can do, or you can leave it like this, right? Because it's just one use. Right? What about the left-hand side there, though? Yeah, that calories is what kind of variable? It is a pointer. We need to make it into a regular old variable, and so that we can assign its value, and so we dereference it. Right? Same thing with the rest of them. BTUs is equal to joules times this thing, right? And foot-pound force is equal to joules times that thing. All good. If you want to, you can go ahead and align them up and make it look real nice. There we go. That's not necessary, but oh, that looks nice, doesn't it? Right. Okay. So let's actually test this. Right. So I'm going to need a testing function here. I'm going to include the standard input, the standard library, include the standard input-output library, and if I'm going to be testing that function, I also need to be including the midterm header file. Right, there we go. Otherwise, it's main int argc char argv. Is dereferencing like a toggle? That's a question online. I'm not sure. A toggle usually is like an on-off switch kind of thing. Dereferencing simply means that you are, for the purposes of that expression, you are temporarily changing it into a regular variable. It's not a permanent change. Right? All right, so return 0. I'm going to want to call this function on some input here. So I'm going to need, say, double joules. All right, I don't know, how many joules did you eat today? I don't know, 10 joules. Right? That's probably way more than 10 joules then. All right, so we've got double joules, we've got calories, and BTUs. How many BTUs did you eat today? BTU and what was it? Foot-pound force. There we go. And I want to convert joules into the other three. So calories, BTU, foot-pound force. There we go. And if you want to, you can also test that you're returning the correct error code. Right? Printf. This is just ad hoc testing. So I'm just going to print this stuff out to the command line. Right? %d, and then joules equals %f. And that's converted to the other three, %f, 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 and the line. And all I need to do is cut and paste this code there. Right. That's just ad hoc testing. I'm just testing this really, really quickly as a sanity check to make sure that everything actually works. Okay. Now, how do I combine all these things together? I need to compile, so -c, the midterm library, right, .h, and don't forget to include the wall flag. Okay, we've got some issues to take care of. Null, error, it's undefined. I certainly use that here, but where is it defined? In the standard library, right? So, for the longest time now, when you've been using the main, right, and you've just had one file, I've told you to include it, but you haven't had to explicitly include it because it's provided to you automatically in 99% of the cases. But now that we're using multiple files here, you need to actually explicitly include it now. Do I use anything else? Do I use math? Do I use input-output? Not in this file. Right? Don't include things that you shouldn't be including. But what should I include? My own header file, midterm.h. Right. Thankfully, we haven't seen it, but that much. But is that right? Midterm.c? Nope. What happens if you do this? Yep, endlessly copies itself in an infinite loop until finally the compiler's had enough, and the compiler's program stack overflows. There we go. So we broke the compiler. I don't know why the compiler can't be smart enough to see that, right? And say, do you really want to include a source file, right? All right, so fix that and compile, and we're good to go, right? I need to bring it all together to create an executable with midterm.o and midterm_tester.c, right? And of course, I should be using the wall flag, but I've got some errors here. Foot-pound-force, did I misspell it? Oops. Foot-pound. Oh, good. All right. So, what's it complaining about? Incompatible type, argument 2. It's complaining about calories, BTUs, and foot-pound-force here, right? It's saying that these are doubles, right? But does the function expect doubles? Nope, it expects a pointer to a double. So just the opposite here. How can I take a regular variable and turn it into a pointer variable so I can pass it by reference? Ampersand. 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 There we go. And now we're good. So 10 joules, all you need to do is look at these figures and, shift the, float the floating point over, right? So it should be 2.39, et cetera, 2 zeros in the 9, and 7.37 foot-pounds force. Right? There you go. Right. Looks good enough to me, and also the code, by the way, is 0. If you wanted to, you could test this ad hoc testing, change that to -10, compile, and what should you expect now? An error code of 1 or 2, whatever it was, 2. There we go. Right. And then, of course, meaningless values for the other 3 because you didn't actually compute anything because there was an error there. Right? Questions on that one? Yeah, go ahead.
You want to have your return values like 0, 1, 2, you want to name those like no error?
Yeah, this is no error means 0, right?
Yeah, but then like when you get that, there's that list that.
You could do it enumerated type. You could do something like type def, enum, ... right? Like you've been doing if you want to. Otherwise, I'm just quick and dirty here.
You put that in a header file then?
Yeah, you generally put that in a header file. Yep. All enumerated types belong in header files. Generally, if you wanted to do it using a define instead, no error, 0, then you would put that in the header file as well. Player's choice. Okay. All right. We're going to write a bunch of functions that operate on what are called bit vectors, right? So what is a bit vector? A bit vector is just an integer array that contains only zeros and ones. 0, 0, 0, 0, or in this case, 0, 1, 1, 0, 1, 0, 1, right? And 1, 0, 1, 1, 1, 0, 0, 0. If it contains anything else, it's not a valid bit vector. We're going to want to make sure that we do some error checking here, that if you gave me just an integer array that contained 5 and negative 42 and stuff like that, that's an error. That's not a bit vector. We're going to want to return an error code in these cases, okay? But otherwise, the first one is that we're going to compute a parity. Now, the parity is used in a lot of applications as a checksum, or as a very, very simple checksum, right? So when you transmit, say, a bit vector over a noisy channel, like the airwaves, or when you record it on a disk or something like that, right? You want to make sure that, that the data was preserved. So one way of doing that is by computing the parity. All you have to do is count up the number of ones. In this case, there are 4 ones. That is an even parity. And so an even parity is going to be associated with 0. This bit vector has only 3 ones. And so it has an odd parity, and so its parity is 1. Right? And it's a way to just have a very easy sanity check that you could detect every single odd number of errors in the transmission by using only 1 bit, right? By computing the parity up front and then setting the parity on with it. Right? So you could actually you can actually do quite a bit of error handling, or error detection at least, with just one additional bit. Right? That goes into coding theory. Okay. All right. So all we have to do is, given this bit vector, 1, we want to make sure that it's a correct bit vector, and 2, we want to count up the number of ones, and if it's odd, then we return, then we set this parity over here to 1. Otherwise, if it's even, then we set it to 0. Okay? So what I want to do first, though, is some basic error handling, right? What I'm going to do is I'm going to write a function here to validate. Now, this is not required as part of the exam, but we've got time to do it. Validate a bit vector. Right? So what I mean by that is this is going to return. Let me go ahead and document so that I can explain what I'm going to do. Right? Examines the given input array of integers and verifies that all values are either 0 or 1. Right? If it is a valid bit vector, returns 1, right? True, right? It is, in fact, let me rename it. Is valid bit vector. Because it's a question. Is it a valid bit vector, right? True, yes, it returns 1. Otherwise, it returns 0, false. There, I like that. Now, how are we going to take this bit vector? It's an integer array, so int star. But what is that const in front of it? Means that you can't change it, right? That's a very good thing, right? You're not allowed to change a value that you give to this function. That it's basically a promise. I will not muck with your data, right? And of course, we need also what is the purpose of this variable right here? If you give me an array, you also have to tell me what? How big the array is. So let's write this really quick. All I need is a valid, well, let's do some basic error checking here first, right? If bit vector is null, or if n is less than 0, right? Can that, now this is not an error code, right? I can't return an error code because that's my return value here. Unlike this function over here where the actual return value is being passed, or is being computed using this pass by reference variable, and the return value is being reserved for an error code. That's not how I design this function. But think about an alternative here. If the bit vector is null, or if it has an invalid size, is it a valid bit vector? No. So return what? False. It's not a valid bit vector. Right? Okay. Otherwise, what I need to do is an idiomatic for loop for each element in the bit vector, I++, if bit vector of I is equal to 0, or bit vector of I is equal to 1, then it's A-OK, right? Right? That bit is A-OK, right? Do I want to return true at that point? Return true? No. Have I checked all the bits yet? No, I've only checked the ith one, right? And if the first one ends up being 0 or 1, that doesn't mean that the rest of them are valid. It could be 0 and then 5, 5, 5, 5, 5, right? I don't want to return true yet, right? So, ideas. Okay, do nothing. Do nothing. Dot, dot, dot. Otherwise, if it's not a 0 and it's not a 1, then return what? False. It is not a valid bit vector. The ith bit is not 0, nor is it 1. Right? Is there a way that I can improve this code so I don't have a dead block here? Negate this. There we go. Now don't do nothing. Return 0 here, right? Return false here. Okay? Does anybody know how to negate this even further? Simplify it even further. If it is, read this out in English. It is not the case that the bit vector sub I is 0 or that the bit vector I is 1. It's kind of verbose. How can I say that? What's an alternative English way of saying that? If bit vector sub I is not 0 and it's not 1, then we've got a problem, right? So do you see what happened to that negation when you distributed it, right? What happens with an algebraic expression here, a plus b, when you negate it? What does it become? Yep, negative a, negative b, right? Plus negative b, right? So these things get negated, but also the or becomes an and. Now I think that some of you are taking some digital logic design. Yes? No? All right. That's called what? De Morgan's law, exactly, right? Not the rum. Is the rum De Morgan? No. What is the rum? Captain Morgan. There, thank you. It's not Captain De Morgan, so it's I sometimes get those confused. Anyway, there's De Morgan's law, right? Helps you simplify your code, and arguably that's easier to read. If the bit vector, if the ith bit is not 0 and it's not 1, then we've got a problem, right? Otherwise, if you get through all the bits and they're all either 0 or 1, then you can go ahead and return true that it's a valid bit vector. Right? I like this because looking forward, we're going to use it here and we're going to use it here. If you're going to use it in more than one place, you probably want to put it into a function. Right? All right. Now let's actually write this function. Okay. So to remind ourselves here, we're going to compute the parity. If it's a valid bit vector, then we go through it and count up the number of ones. And if it's even, then the parity should be 0. If it's odd, the parity should be 1. Right? That should be fairly simple now. Right? So if it is not a valid bit vector of bit vector and n, then return 1. Right? Some error code here. Now, is that the only, do I need to do any other error checking here? Remember that this is already checking for null. This is already checking for negative values here. So we're good to go on these first two values here. But what about this one right here? Yep, always check for null. If parity is null, then I'll return, I don't know, a different error code. Same error code, doesn't matter. As long as it's non-zero. Okay? All right, now all I have to do is count up the number of ones. Suggestions? Probably want to create a counter variable, right? All right, so count ones, all right? Or I'm going to put it as num ones, right? Number of ones. Number of ones. Depends on how verbose you want to be. Num ones is good. Right. I've already made a mistake. Initialize all variables. Right? Make no assumptions about what's stored in a variable. Dead beef, garbage, right? Whatever is in there. Now I'm going to go ahead and go through each one. Idiomatic for loop here. For int I equals 0, I is less than n, I plus plus. Right? If the bit vector of I is equal to 1, then I will increment my counter, num1s plus plus. There we go. Now, if the number of ones is even, then I set this parity up here to 0. So, if num1s is even, then I will set parity equal to 0. Right? There's my start. Translate this. Can I is even? that's not built into any language that I know of. Right? So num1s, how do I determine if it's even or not? Divide it by 2. If it's even, its remainder should be 0. This is also wrong, but for different reasons. Let me try to compile this really quick. There we go. Oh, you didn't catch that? Stupid. All right. Why is the... what about W extra? Nope, you're not... I can't believe that you're not catching that. Anyway, what's wrong with line 51 here? Dereference it. Why? Because it is a pointer variable. In order to set it equal to a value, you need to dereference it. I bet I can get you to finally detect it if I set it to... Yep, there we go. There. This is why it's so important to make a distinction between 0 and null, because the compiler don't. Right? The compiler is sitting here thinking that, oh, that last one where you set it equal to 0, that's perfectly fine because you must have meant null. So I'm going to go ahead and assume that you know what you're doing. Right? I'm not going to give you a warning at all. Right? This is why it is absolutely vital to make sure that you're not conflating 0 and null. Right? We've got a lot of different notions of nothingness now in C. Void, 0, null, what else? 0. We'll eventually have the null byte when we look at strings next week, and a couple of other things. Void star, right? The generic void pointer, right? But this is why it's so important to make sure that you're not that you're keeping all those straight, because the compiler will not help you. Right? The compiler here was absolutely wrong. I don't want to set it to null. I want to dereference it so I can set it equal to 0. Right? Else, it must be odd, and so therefore the parity should be 1. Excellent. Let's do some ad hoc testing here. Make sure it compiles first, I guess. Excellent. Right. Come back over here. Let's create a bit vector. Let's see, int a is equal to, I just cut and pasted this from the handout. That has 1, 2, 3, 4 ones, so therefore it should have an even parity, and the parity value should be 0. Int parity. Let's go ahead and call that function there. Compute parity, all right, of a, and oops, let me go ahead and go n here too. It's of length 7, right? N and parity. Why did I put an ampersand in front of parity? It's a regular old variable. The function expects a pointer. So to make it into a pointer, I put an ampersand in front of it. Let's print out the results. I don't care about the error code anymore. Well, I guess we could. Fine. Let's be thorough. Code is equal to %d, and then parity is equal to %d and the line. Code and parity. Now, if this is correct, I should have gotten 0 and 0 for this, right? Compile that with extra. Yeah, okay. No, not with extra. A dot out. There we go. So, no errors, and the parity was 0. Ad hoc testing. Let me go ahead and do it with another one here. Int b is equal to this thing. And let's go ahead and put in B instead. This should have, it has 3 ones, and so therefore it should have an odd parity, and and parity is 1 now. I'm convinced that works. Okay. Write a function to compute the Hamming distance. I must have been in a coding theory state of mind when I wrote this. Both of these things are used in coding theory. Coding theory is not like as in coding, like you're coding in C or coding in Python or something like that. Coding theory as in information theory, where you either add redundancy to data in order to preserve the integrity of that data, or you want to compress the data so that you can store it, get rid of redundancies. Right? A Hamming distance is used for Hamming codes, so where you can add like a logarithmic amount of additional information and then actually do error detection and error correction in codes. Right? When you're transmitting through a lossy medium like 802.11g or whatever, has anybody ever tried to be on their computer or be on their network and stand next to a microwave? All right, what happens? It dies. Why? Because it's on the same frequency, microwave frequency as 802.11, right? Or very close. And so the microwaves are going to be interference, and so your data gets garbled. If it's only slightly garbled, then something like a Hamming distance code or a Hamming code can actually fix that stuff at one end without retransmission. But if you've got a lot of noise, then you're resending everything, right? Or making sure that you reconnect back to the network after your burrito has been cooked, right? All right, so the Hamming distance here is simply a measure of between 2 bit vectors, right? These are the same bit vectors as before here, but they differ in 3 spaces. That's the Hamming distance. The first 3 bits agree, 0, 1, 1, 0, 1, 1. But the 4th bit, one of them is 0 and the other one is 1. One of them is 1 and the other is 0, right? So they disagree in those 2 bits. 0, 0, they agree right there. But 1, 0, they disagree. So in total, they disagree in 3 spaces, in 3 bits. That's the Hamming distance, okay? All we need to do here is iterate through the bit vectors and count up the number of ways that they disagree. If they're both 0, fine. If they're both 1, fine. But if they're 1 is 0 and one's and the other one's 1 or vice versa, then we need to count that up. Right? Put my header, or put my prototype over here in the header. Right? There we go. And then put my definition over here in this file, Hamming distance. Right? So the first thing I should do is some error checking here. I'm going to steal that code from up there. And this is why I wrote it in another function, right? Because now I can reuse it. So if bit vector A is invalid, or, let's see, or is valid bit vector, it is not a valid bit vector of bit vector B of the same length, then I'll go ahead and return 1, right? Now I know that both of them are valid bit vectors. What else could go wrong? Ham distance is null. If that's the case, then return 2 or something else. Otherwise, everything's hunky-dory. Go ahead and return 0 here. All I need to do now is count up the number of ways that they disagree. So for int I equals 0, I is less than n, I plus plus, right? I need a counter here. If bit vector A sub I is not equal to bit vector of B sub I, then I'll go ahead and increment my counter. Num bits, they disagree on plus plus, right? Now wait a second, Ham distance, that's my counter, right? So all I need to do is go Ham distance plus plus, right? Ham distance is a pointer, right? So is this going to work? It's pointing memory location 124. plus plus, what is it now doing? Pointing at memory location 125, plus plus, pointing at memory location 126. Right? It's not doing anything except for changing your pointer and what it points to. And it's doing it wrong. Oh, okay, thanks. You now reminded me that it is indeed a regular, that it is indeed a pointer variable, so we should have dereferenced it first. Right? That's still wrong, right? Because if you take out your big book of PEMDAS, PEMDAS is what? Parentheses, order of operations, parentheses, exponents, multiplication, division, the rest of that stuff, right? There are two operations here. There's a dereference operation, and then there's a plus plus, an increment operation. What does my big book of PEMDAS say? Which one has a higher order of precedence here? Right? I don't want to have to remember that crap, because even if I did, it would end up being something like this, right? That's equivalent to what I just wrote, which is still wrong, because you're taking the pointer that's pointing at memory location 125, moving it over to 126, 127, 128. Right? Okay, fine. Do the dereference first, and then you can increment. Right? Well, technically this line is now correct, but it's still wrong for what other reason? Yeah, what was in that variable to begin with? What do you start a sum at? 0. What am I assuming about that variable? I'm assuming that it started at 0. That assumption is not valid. Fine, go ahead and do this. Ham distance is equal to 0. Now it's correct. We would not have gotten into this situation and made those 5 different distinct errors if we had just followed a better style to begin with. Don't play around with pointers unless you have to. Int num bits disagree, or num diff bits, let's say. Num diff bits is equal to 0, and then num diff bits plus plus, right? Is there any ambiguity here at all? Right? Is there any assumption at all? No, nothing, right? I didn't have to deal with the big book of PEMDAS. I didn't have to deal with an assumption about what was in that variable. I didn't have to deal with any of that noise because I'm just using a regular old variable. Play with pointers sparingly. At the very end, of course, ham distance, you'll have to set that to num diff bits. But you're done, right? I avoid, the engineering is all about KISS, right? Keep it simple, right? The keeping it simple means reducing the number of failure points, reducing the complexity. Right? By using a regular old variable, I've eliminated 90% of the guesswork. I've eliminated those 5 potential failure points of me forgetting what the order of operations were, of me forgetting that there can't be any assumptions about what's stored in a variable, et cetera, et cetera, et cetera. Right? Very, very nice here. So let's go ahead. I've already got my bit vectors here. Let's go ahead and compute the Hamming distance between them. Remember, the Hamming distance should be 3, right? Because it disagrees in 3 locations, A, N, M, and ham H dist, let's say. Int H dist, Hamming distance. Right? And then we'll print that out, printf. All right, fine, code is equal to, code is equal to %d, and then hdist is equal to %d and the line. Oh, sorry. Oh, sorry, I meant b, right? A, b, and then they're both of size n. Thank you. Hdist. There we go. Compile everything, starting from the midterm, then everything else, run it, and if it's successful, then it should output 3. Yay, it does. Okay. Excellent. Last one, vector multiplication. So as an example here, suppose that I have the values, let me go ahead and come over here to my tester and do some TDD instead. TDD is test-driven development, where you write the tests before you even write the code, pedantically so. So let's go ahead and go with vector A. if I've got, say, 1, 2, 3, 4, and 5, right? And here I'll reset n here to be 5. And then I've got another vector here, vector b, and it's, say, 10, 20, 30, 40, and 50. Then the result should be 1 times 10, which is 10, 2 times 20, which is 40, 3 times 30, which is 90, and you get the pattern here, 160, and then 250. Right? All you're doing is taking the first components and multiplying them together and creating a new array. Right? The second components and a new value, et cetera, et cetera. That's what vector multiplication is. You take one bit vector and another bit vector. In this case, I've got, I did not restrict them to just bit vectors, but of size n here. And then you return a new bit vector here. Okay? What is that doing if it is a bit vector? Look at this example up here. What if I were to multiply these together? What values would I get? 0 times 0 is 0. 1 times 1 is 1. 1. 0 times 1 is 0. 0. 0. 1. What is that? You folks that are taking the digital logic design. Multiplication with respect to bits is what? Well, not addition, because 1 plus 1 would be, well, it would remain 1. You could think of it like that, yeah. But 0 plus 1 would not be 0, right? So addition has another interpretation, but what about this? Multiplication. It's a logical AND, right? Now, addition is the logical OR, but 1 plus 1, you can't go to 2, so you stay at 1, right? So it's ceilinged out, or whatever, whatever that. It's kind of like the logical OR, right? So this vector multiplication here, when it's a bit vector, is actually just a bitwise OR operation, or bitwise AND operation, excuse me. Okay. Let's come over here. Here is my prototype. Come over here, and I'll let you do error checking on your own. To do error checking. Dot, dot, dot. Same thing as before. And by the way, another pattern that we've seen, not necessarily in this section, but in other sections, is for some inexplicable reason, people will do correct error handling on function A, but then do no error handling on function B, right? And then everything is still segfaulting out because they did selective error handling. Error handling belongs in every function period, okay? All right, so error handling, we'll do that later. Right? Otherwise, vector multiplication here, the thing I want to focus on is the fact that we have to create a brand new array and return that brand new array. So to do that, I need a new integer array here. Result, right, is equal to a call to malloc that I typecast. What do I give off to malloc here, though? N, all right. And there, so I want n integers, say 5 integers, but is that how many bytes I want? Nope, I want n times 4, 20 bytes, or however many bytes an integer takes. And then I can return that result, okay? Otherwise, in result, now I need to fill it up with values. So for int I equals 0, I is less than n. The idiomatic for loop, I plus plus, right? Results of I is equal to bit vector of A sub I times bit vector of B sub I. That's it. Right. Cool. What about error handling here, though? So if bit vector of A is null, remember I did write that function, but I want to do something else here for a second. Or bit vector of B is null, or n is less than 0. I'll return a non-zero error code. No, why? What is the return value here? That's not an error code. That's a pointer, right? If I return 1, what am I telling the calling function? Yeah, look at the memory address 1 for your results. Right? That doesn't necessarily even exist. Certainly, it is unlikely that it belongs to this program. Right? So, what's the only thing that we can return to indicate that something went wrong? Exactly what malloc returns. Null. All right? There we go. Let's go ahead and come over here and look at our result. What was it called? Vector mult. Right? So, int c is equal to vector multiplication of VA, VB, n. And now I can't print it out nicely here. Instead, I'm going to have to write a loop to do it. For int I equals 0, I is less than ni plus plus. Return printf %d space and then c sub I. And then at the end, printf end the line so that it looks nice and pretty. Right. Compile this, compile that, run it. 10, 40, 90, 160, 250. Okay. Why did I have to write these 4 lines? I don't want to do that. Right? So let's not do that. Okay. Let's remind ourselves of the tool that you're going to use in today's hack. Okay. I want to know what the contents of that result is. Right? Maybe there's something going on. Maybe there's something wrong with it. For example, we forgot to return the result. We returned 0 instead. Right? So let's go ahead and recompile. Recompile. And yes, thank you. And, oh, come on. Oh, unused. All right. Restore that loop. There we go. GCC. There we go. Now I'm probably going to get a segmentation fault here. Thank you. Yes. Now, in an ideal world, Bret Hart would be stepping out of the computer right now and smacking me upside the head. We do not have an ideal world here, so instead we have another tool. Couple of tools. The first tool that we run is valgrind a.out to find out what the hell went wrong and where. Except that all I see are a bunch of vector mult in a.out, main in a.out, etc., etc. What did I not do properly? Compile it with -g, exactly. So compile the midterm with -g, compile everything else together with -g, and now I can run valgrind and it'll tell me exactly where it segfaulted out. On line number 85. Line number 85 in midterm.c is right here, right? Actually one block. Oh no, sorry, that's the memory leak right there because we never actually freed it up. Where's my actual seg fault here? Here we go, right? Midterm tester at line 31. We tried to access something C sub I that there's something went wrong here, right? It's telling me that it's not stacked, it's not malloced. I wonder what value it has. So I know about where it is. I know that it's about on line 29. What's the second tool that I can use to then stop my program and take a look around? GDB a.out. Right. Okay. I'm going to set a breakpoint at line, 27. There we go. Layout source because I want to see what's going on. And let's run it. Refresh. There we go. So now I'm stopped at line 27. Right? Line 27 is up here as well, but this is the actual debugger down here. Let's go ahead and go with next. Next. All right, so I know something went wrong with C, so print C. Oh, it's 0. That means null, right? It is null. Like, okay. If I try to dereference that, print whatever is there. It cannot access that, right? So something went wrong. Let's go ahead and rerun it from the start. And before we go over that line, let's go ahead and step into that function to see what's going on. Sometimes you have to refresh. Next, 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 next. Okay, so it's successfully going around into this loop here. Now, before we go back to the calling function, let's print out the result. That's a valid memory location. if I want to print the result of an entire array, print result, or dereference the result, and tell it how big it is. I think it's 5, right? I don't need to guess. I could just use the variable n. 10, 40, 90, 60, 250, 160, 250. Those were the results that I expected. But what am I about to do now on line 90? I'm about to not return it. Next, next, refresh, and print C at n. Right? Can't access that memory. Why? Because we didn't return it. Right? Again, don't conflate 0 with null. You'll get yourself into trouble because this is you're trying to return a pointer here. Unfortunately, the compiler is assuming that, okay, well, you must know what you're doing here, and you must know that you're going to use 0 for null. Don't do that. Right? Make sure that you're always using explicitly null so that you don't fall into that trap. Right? Quit, yes. GCC everything again, and even with the G flag, run it, and oops, come on. Midterm. It's slow to save, that's why. Oh, come on. Did I not save it? Oh, what am I doing? No. Result. Right. There we go. There's the original. 10, 40, 90, 160, 250. Right. So even just using a GDB as a tool so that you don't have to write a bunch of printing code, right? We've given you print code before in the past so that you could print out the contents of an array conveniently, but GDB is an excellent tool that you don't have to write that boilerplate kind of crap and then erase it, right? It's a really, really nice tool to use. I'm sure that if I ran Valgrind now, I would get no errors except for memory leaks. Yep, there we go, Valgrind. There are going to be memory leaks here of 20 bytes. Why? Over here in main, this array that we allocated. Once we're done with it, I should clean it up. Free C, right? GCC, and run it again through Valgrind, and there will be no memory leaks at all. Right? No errors, no memory leaks, nothing. Right? Okay, no questions online. Any questions here? But yeah, go ahead.
I'm sorry, how do you make it so it like prints the code so you can go step by step with GDB?
GDB. Layout.
Layout.
SRC. Source, SRC is short for source, right? You can either do other layouts, right? You can look at the, do you do assembly yet in your digital logic design? No? Okay. Then you never want to look at assembly anyway. Layout, and then go back to layout source. There we go. That's what you want to look at. I don't know, layout, how do you get explicitly to just assembly? ASM maybe? Yep. ASM is short for assembly. Layout, both? Nope. Layout. ASM, next, previous, regs. That's for the register layout. Split and source are your options. Right? So you can also ask for help. Right? Help layout. Right? And it'll tell you that here's a list of standard commands. Right? Help, step, right? Usage, step, n, argument n means that you can actually step n times, right? So help, next, right? You can go next, 10 lines. Jump ahead 10 lines for me, right? Or whatever. There's no program being run right now. So you can ask for help like this. Yes, the midterm is open book, open note, open computer, whatever you need, right? All right, no questions? Okay, then in your hack today, you'll be using GDB to debug a tic-tac-toe program where you can play with your partner, you can play alone against a dumb AI that's just random and maybe win at tic-tac-toe, or you can play against the smart AI that you'll never ever beat, because tic-tac-toe is a rigged game. Right? It's a solved game in terms of game theory, right? All right, I'll see you over there then.